Okay, last chapter. Chapter 15. Okay, so we're doing simple harmonic oscillation stuff. It's kind of a little bit of a review stuff added with some new stuff. Simple harmonic oscillation. They call it SHM a lot, or SHO. That has to do with like your springs. The spring lab we did, you should have done already. I think it was like lab 12 and 20, I believe. So those are simple harmonic oscillators. The other type that we use a lot are pendulums that swing back and forth. And a lot of things that we do on the atomic level have to do with these single harmonic oscillators. So we'll get to that later on, but basically we can look at the oscillations of individual atoms as single harmonic oscillators. They're just oscillating very, very, very tiny. Okay, so there's a bunch of introductory stuff here, but I'd rather just go through it. So the frequency, we've used this before, this equation here. You have the period is equal to 1 over the frequency, or vice versa. The frequency is equal to 1 over the period. Remember, the period is one cycle of something that it goes through. And then we have this equation down here with a cosine in it, right? So simple harmonic motion is periodic motion that is a sinusoidal function, right? So essentially, swinging back and forth, if we model it out, it just makes a sinusoidal function that I'll just kind of half draw there. But you have these components in it, and we've seen most of these before. You know what a cosine function is, x being the distance on the x-axis. You have your omega, your t, and phi, which we'll get into more here in a minute. One other thing, I guess real quick, is that you should have been using this for frequency before, but the unit of measurement for frequency is 1 hertz, which was the guy's name that came up with it. So that's just 1 oscillation per second. I, for some reason, always keep that definition in my mind, what a hertz is. It's 1 oscillation per second. Sometimes it helps you conceptualize what's going on. So here is, like everything from these are from your book. Here is an example of modeling a simple harmonic oscillator at each point in time that we're looking at it. So it's, for instance, a ball oscillating in some fashion, whether it's a pendulum or a spring bouncing back and forth, and we're taking snapshots of it through time. So you can see on the x-axis here, it's the farthest most in the plus direction on this side, right? And then it's swinging back towards the minus side. And I think it says somewhere in here, they call them extreme points, a couple places in here. But the extreme points are also turning points, right? So when it hits these extreme endpoints of the positive and x, the max distance it goes, they can also be turning points, right? This is when the object that is swinging on a pendulum or a spring is turning in direction and going back the way it came. So this is 1 full cycle. It starts at this maximum positive x, it swings through to a maximum negative x, and then swings back through to a positive x, and then this cycle just repeats, right? Comes down, comes back down, back to the positive x, etc. And then we have it doesn't give, we're just using a variable, right? We don't care actually for example purposes how long that the period actually is. We're just saying that when it gets to this point, it's a quarter of the total period. When it gets to this point, it's 1/2 of the total period, right? 3/4, 1 full period here. So this is going through 1 full oscillation, right? And then this just shows you the velocities changing directions, which I just talked about. And then basically we're just taking that whole thing and we're rotating it so it's up and down, because then we can start simulating our sine wave, right? That's how we're getting the sine wave for it over here, which is drawn here. And then you can see that wherever we start on the x-axis, where we end is 1 full period. So it goes through the full motion, comes back, and right where it started, is one full period, or one full wavelength if you're using wavelengths. If I were, for instance, continue this down and bring it back up, if we say we started here instead, then one full period would go to the second trough, is what it's called. So you got the trough to trough. These are generally called the crest at the top of the wave. So if you go, for instance, from the crest to the crest, it's one full period. You go from trough to trough, it's one full period. You can go anywhere, right? You can start right where it's 0 on what they're calling this x-axis. It's going our normal direction of y, but if you start there, you can also end there, right? So this is also one full wavelength between them. So one full wavelength or one full period isn't necessarily has to start in one place. It's just the same distance shifted around. Okay, so the how far the particle moves in either direction is the amplitude. In this case, we're looking at the amplitude up and down. So if you look where the x-axis is 0, and then we look up, this is the amplitude going upward. And we can look at it in the negative direction going downward. It should be equal on both sides. And then what they're talking about here, the argument of the cosine is the phase. The easiest way I like to explain this is if you have a starting point, let's say this is x is 0 here, right? The starting point of this, so it's a maximum positive x is the starting point of this wave. If we were to take that wave and say it starts here, and then we shifted the whole wave over. So now we redraw our axis, and then we say now instead of the top of the wave is now over here, and it's coming down like this, something like that. Slowly getting better with this stupid pen thing. It's taken me pretty much all semester to be able to draw reasonable lines with it. But see, the original starting point was here, and now we've shifted it to here. So we've moved the phase angle now that's measured between them is now changed. This is essentially what changing the phase angle is. If you guys had done a lab with, if you end up taking 181, you'll use what's called an oscilloscope, which measures electrical currents and voltage, and it will display it on the screen in the form of a sine wave. Well, at least if you set it to show you a sine wave. But you can change the phase angle by shifting it back and forth, right? So depending on what you do, you can start out, you can change like the initial voltage of something, because where the phase angle starts is also where it correlates to the voltage, right? So this is just your phi. This symbol here looks a little different, it's a little fancier. It's just this guy down here, as you're probably more used to having. And again, they call this the phase angle. When time equals 0, then you're setting it just for the initial conditions, right? This says it here. And then we have, again, the angular frequency is this omega, which we've used before. Okay, so we have another equation here. This is pretty useful. Omega is equal to 2 pi times the frequency. 2 pi, remember, that's usually your transition between radians and degrees. So you can also take 2 pi and divide it by the period, and then remember that the 1 over period is just equal to frequency, so it's the same thing, right? So this one, they've taken basically two similar waves, and they've overlapped them on top of each other, and they said that the frequency and the period are the same, but then the amplitudes have changed. So you can see the blue wave here, amplitude goes up this high, pink wave, amplitude goes up this high, right? So it's just extended the amplitude. But where the crest or top of the wave occurs is on the same place on this T line or timeline. Same thing with the trough here. It occurs in the same place, right? So they're in sync as far as frequency and period go, but they've changed because of the amplitude. In this case, they've made the amplitudes the same, so they reach the same height on the x-axis for both blue and pink, but then they've made them out of sync. They're out of phase. So the corresponding peaks and troughs, or crests and troughs, don't line up. So you can see they do on some places, but they don't, for instance, over here. So it's because it's out of phase. So it'll match up sometimes, but not all the time. Over here, they're in phase, so they have to match up every time. So then they're just talking about the negative values, so saying, you know, the direction it's heading in, so you get a negative value. So yeah, so this is a phase shift too. So this is probably easier to see between the blue and the pink. The blue is sort of a classic cosine wave where it's starting out at the peak is right on the x-axis, and then we've decided to shift the blue by changing the phase angle by the negative pi over 4. That's telling us how much out of phase it is. It shifts the phase of the wave forward like that, so that it's a little out of phase from the other one. And again, there's multiple uses for this. A lot of this has to do with electrical engineering. You can use it for other things in this too, but it's sort of an everyday application if you're an electrical engineer. Okay, so a particle undergoing simple harmonic oscillation of period t is at negative xm at time equals 0. This is figure 15-2, so we go back a couple slides. That was this guy, figure 15-2. And if we notice at time equals 0, our picture here is on plus, or the positive xm. So go back to the question here real quick. At time equals 0, it's at negative xm, right? So all they've done for this question is say that the starting point is now here, right? And then it's going to go through the same pattern and go to 1/2, and then go down to t. So I didn't draw my line exactly straight there, but it should go to this t here, right? So it's just saying that it's doing the opposite. So it's kind of checking your understanding of what's going on, but the exact same thing's happening. Is it at negative x, positive x, 0, somewhere between these things when t equals 2 periods? So we go back, and then basically they're saying when this equals 2t. Okay, so I tried to erase this red line, but it's not working. So again, we are starting at the 0 point here. We are bouncing through sort of the mirror reflection of this, going back to time t. Then it's going to go through another full cycle here, and then bounce back down. And if we extend this line down, essentially this would be 2t down here. So the line, we'll just make it like that and say that's there. So we can see at 2t, it's on the negative x, right? It's exactly where it started. It's exactly where it was at the first period. It's exactly where it is at the second period. And it's going to keep doing this. It's a repeating pattern, right? So it's going to be 3t, 4t, 5t, etc. So we go back to the next part. Where is it at 3.5t? Look at this again. You can just put the 3 here. It's still a half. It's going to be, in this case, at the positive x. So the first answer is, this should be negative x, positive x. And then where is it at 5.25? 5.25 is just going to be a quarter. So it doesn't matter, it's times 5. It's just going to be at 0. So this is 0. And it just erased my thing because it's on the other slide. But see, negative, positive, 0. Okay. So we have this time derivative of the position function. And the position function was your x equals x times sine. That was supposed to be cosine. Let's try this again. X equals x cosine omega t plus phi. So this was your position function before. And then if you take the derivative of it in respect to time, then you're going to get the velocity, right? So you do your derivative of your cosine, and you have to take the derivative, and that becomes negative sine, right? That's where this comes from. And then you have to also take the derivative of what's on the inside. Time is only attached to the omega portion, so time goes away because you're taking the derivative. Omega pops out. That's where this comes from, right? So that's one derivative. Just like the original kinematic equations we did in chapter 2, if you take a second derivative, you're going to get the acceleration, right? We're going to get an omega squared here. This is going to switch back to cosine. And I think we'll show that in a bit here too. That'll come back up. So you have the velocity amplitude is what this equals. Okay, yeah, it's on the next slide. The acceleration can be found just by taking the second derivative, what I just explained. And then you get the omega squared, etc. Goes back to cosine. Remains negative, because that's how it works. But so you get the acceleration amplitude. They're saying that essentially your angular portion is here, and then this portion is the amplitude. So if you were to take a wave and you want to change the amplitude, you're going to put a coefficient in front of this. It can be whatever. It can be 3, 4, 5. It can be this function out here. But that's going to change the amplitude, right, up and down. So however this changes, that changes the height of this guy. And then acceleration related to the position is then just this portion, right? It's exactly this this coefficient normally. In this case, it's variables. That's going to be out front, and then that can just be related to the position. Okay, again, we like to take Newton's second law and then incorporate what we're doing and make that fill the Newton's second law. So here, you're just going to take mass times the acceleration, right? So you get mass here. We just established this is acceleration from the last slide. And then you can just distribute that negative to both because they're just magnitudes multiplied by each other. So by doing this, we're saying that this is similar to k and x. So now you're getting a negative out here, and then the force equals to this. So we're saying that this is equivalent to Hooke's law. We have a restoring force. So it's a negative out front here. You have some coefficient, and then you have the x variable that we're using. So again, one of these little star things. Simple harmonic motion is the motion of a particle when the force acting on it is proportional to the particle's displacement but in the opposite direction. So that negative sign becomes very important to the definition of this simple harmonic motion, right? Because it needs to be able to go back. It can't just swing in one direction. It's got to be able to go back and forth. So some of the simple harmonic oscillations, we're going to get into like the little pieces here. So we're looking at this, and we have these pieces, so we're defining basically what this omega is. So when you have the omega there, you've got the square root. So if we plug this back in for this omega up here, you can see it's squared, then the radical goes away, and you're left with k over m, and then the m's cancel, so all you're left with is k. So by equating this to the Hooke's law, you can get that angular frequency is equal to these pieces of the puzzle. Again, it's more information, so if you have this equation and you're missing different pieces when you're doing a physics problem, you can always refer to this equation, and hopefully it helps you solve things. Same thing with the period, 2 pi, and now we have the inverse of this. You have m over k. Which of the following relationships between the force F on a particle and the particle's position x gives a single harmonic oscillator? So basically, what is F equals negative kx is what they're saying here. If I can draw this properly, looks a little goofy. So obviously this fits it pretty well, right? We have a negative sign out here. We have a coefficient of 5 that fits in the variable here for k, and then you have a portion of x. This one, negative kx, actually also fits it, but this is an exponential. So I think it should actually give it just doesn't give a linear version of it. This is an exponential, so it's not linear. This has no negative, it has no restoring force. This has no negative, no restoring force. So the thing we're looking at here is basically the first one, A. Yeah, so they're going to add this little adjustment here that it is non-linear, but it is actually still harmonic motion. It's just non-linear. That means it's going to not move at a constant rate. It's going to speed up. It's going to like zip and then slow down, etc. Okay, so looking at more spring stuff. So now we're going to get back into the energies. So here you have the potential energy. Here you have the kinetic energy, right? These are the two totals we need for the total energy. Remember, you have conservation laws and stuff, so these things add up. It must be the total energy of the system. So again, that limits the information, and you can work with it. And what they're doing with these little graphs over here is, so you have this black line on top. So this means the total energy. This is the total potential designated by you, and then total kinetic, right? So the maximum amount of energy has to be at this line. So what they're saying is, let me see, the pink is the kinetic line, and then the green is the potential line. So the kinetic line starts out at 0. That means that the kinetic line must start out at the maximum energy of the system. So if the potential is at a maximum and the kinetic is at a 0, if it's a pendulum swinging back and forth, it must be at the very top of the swing. So our initial position is here at the very starting point of the swing. As it swings through, it is then converting that potential energy into kinetic energy, right? So kinetic energy begins to rise, potential energy begins to fall. Right when they're in the middle, they meet, they're exactly equal, which would be halfway through the swing, like 45 degrees. So if it started at 90, it swing to 45, they would be equal here. And then once it hits 0 at the very bottom, it's lost all its potential energy, and then it's converted it to kinetic. That's if you're using it as a gravitational energy. If you use it as spring, it's a little bit different. So the 1/2 kx squared is then referring to the spring potential energy, not the gravitational. So you'd want to use more springs for this. But that's pretty much the whole thing. And we have one full period it's saying is over here, half period is over here, etc. So again, we have the totals defined as this, and what we did was go through here and we said this is the potential energy, the 1/2 kx squared, which again is potential spring energy. And then we're applying it to the cosine portion of this, so the wave function over here. So you can get all the information out of it. If you notice, then this just becomes sine. It's the same equation, it's just the sine of it for the kinetic. So that's why this is saying that the pink is the kinetic. It starts at 0. A sine wave starts at 0 and then begins to climb. A cosine starts at 90 of that and then begins to decline. So that's why they're saying the potential starts with cosine, the kinetic starts with sine, right? And again, same thing here for like a single oscillation. Another checkpoint thing here. So this is the figure. The block has a kinetic energy of 3 joules. The spring has an elastic potential energy of 2 joules. So that automatically gives us, we have kinetic plus potential equals 5 joules. Right, so we've been given information right off the bat. When the block is at x equals 2 centimeters. So this is at 2 centimeters. Just going to write that like so. What is the kinetic energy when the block is at x equals 0? Right here in the middle. What is the elastic potential energy when the block is at x minus 2? So we're going to have minus 2 is one of the things. And then when x is equal to -2, and then when x is equal to negative x. So saying what is the potential energy. So we have that what was the potential in the beginning? The elastic potential is 2 joules when it is at positive 2, right? So when it's at negative 2 in the swing of things, if we plot this out, basically we said somewhere, I don't know, I'm just going to make it up. We'll say it's right here. It's at 2. So now we're basically looking at the negative portion. So whatever, if you want to make this positive and negative, that's fine too. It's a mirror situation of it, right? So over here it must also be 2. So when it's at, I guess I'm answering the part B first. What is the elastic potential energy when the block is at negative 2? It must be what it is the same at positive 2. And so it must be 2 joules, right? So this one's 2 joules. And then it's saying, what is the elastic potential energy when it is at negative x? So these are the parameters, the boundaries or the limits of the problem, right? This thing is swinging back and forth, and the max it goes is to positive x, and the max it goes the other direction is negative x. So we know that when it hits negative x and positive x, there's 0 kinetic energy. It's a turning point, an extreme point. So everything must be converted to potential energy. So in this case, the total energy of the system we said was 5 joules. Then the total potential at the maximum must be 5 joules, right? And then the first one was, what is the kinetic energy when the block is at x equals 0? So this is in between, I believe, when it's so they're saying that everything's been converted to kinetic energy in the middle. That's the perfect portion where there's no spring energy, and essentially where x is equals 0 is if you let the spring go and you just had the block sitting there. So it's not restoring force either way. You haven't pulled the spring in any direction. It's sitting at its natural resting place. So it must be fully in kinetic energy there. So again, our total energy of the system is 5 joules. So that first one must also be 5 joules. So 5 joules total. 2, it must be equivalent because it's like basically a mirrored situation. And then again, it has to be the total potential. Okay, so here's like a sort of a weird particular situation. This is basically a disc on a wire, and all they're saying is that the wire's hanging on, and then you spin the disc. So as it spins, it tightens up on the rope or wire or whatever it is, and basically spins up like this, and then spins back down. Does that make sense? So if you spin something enough on a string, it winds up on itself and then winds back down. So it spins one way up and then it spins the opposite way down. And it's just doing this over and over. And they're using this to convert things into an angular simple harmonic motion instead of like a linear harmonic motion. So similar to what we did before with the angular stuff, you take the kinetic equations and then just put in the angular pieces, and then you have these new equations. But it's the same idea. So again, you have this piece, and now instead of K being a spring constant, it's now called a torsion constant, which has to do with the wire or the rope or whatever you would use to dangle this from. You can see it's similar to the Hooke's law. We have the negative sign, we have a coefficient out in front, and then we have a variable, and then so on. And then so you get these alternate variables just for the situation. Nothing too crazy. So here we are talking about restoring torque. And what's happening here is you have a ball, some mass. This is the length of the wire or string that it's hanging from. And of course, like everything in 180 physics, it is an unstretchable massless string. It's magic string, right? Because we don't want these extra variables in there, everything becomes really difficult. So you have the length here, and we notice that this is a minus sign towards a coefficient. You have the force of gravity, and then you have the angular coefficient here. Um, Again, like I was saying early on, we actually use this situation for atomic level particles. So we say it's equivalent to a single harmonic oscillator. Um, because it's so small and because the angle in which it's changing is so small, because it's basically just vibrating like this back and forth. Um, what we say is then we use the small angle approximation and we say sine theta is equal to theta. Right? We're just saying the angle is so small that there's no point in using the sine portion of it. We're just saying that it's equal to theta. So that piece goes away. Then we have the force mg as it's stated here. And then again, you have your length. And then you have your inertia portion and that you're dividing by. So it gives you angular acceleration. And then they're talking about it's proportional to position but opposite in sign. So again, more information. And then you have more complicated drawing down here that gives you all the pieces of what we're talking about. Okay, angular amplitude. Again, more pieces. You have, from the previous line, you have the force times the coefficient portion, again divided by the inertia portion. So we had all these pieces. And then, of course, this was basically an omega squared. Come on, pen. And then we got rid of that by doing this to both sides, right? So it just becomes this guy equals this guy. And then we have the period. Again, we've just introduced all these angular portions to change the equation that we know. And then, yeah, they're just saying that this has a more complicated mass situation, but we can simplify it down to a simple harmonic oscillator. So now we're getting back to the like center of mass kind of things, where we get kind of oddly shaped objects. Like this kind of looks like a bowling pin, maybe a really weird looking baseball bat. But it's an oddly shaped thing. It's not straightforward, but we can approximate it as like just a simple pendulum by using the rules we learned before. Okay, so we're going to talk about, again, they're talking about COM, that's the center of mass. Then the inertia will be particular to the mass distribution. Because remember, some of the inertia stuff we learned about was like rolling down ramps, etc. So you have like a cylinder, a sphere, a hollow sphere. They all have different inertia. There's different coefficients out front because of the shape of the object or the density of it, how it's working. Yeah, so then you get the period with these extra pieces. Again, same thing here. You have the force. Now we've just used h to be the distance, which we're just replacing with L, the simple harmonic oscillator length of a pendulum, then inertia portion. So again, same stuff. We've added the 2 pi. Remember that 2 pi times the frequency, and then basically we've taken the inverse of this, so we don't have to do 1 over period, so that's why this is flipped. All right. So more stuff here. Center of oscillation, physical pendulum is the length here. I just talked about that. Can use to be determined G. Assume the pendulum again is a uniform rod, so instead of a string or whatever, because it doesn't bend, it's not swinging, you might as well assume it's a rod. And then we have the pieces that we just came up with, and then these equations that comes out. Yeah, so I think there's a little bit more derivation of this in the book if you need to do it. Checkpoint: 3 physical pendulums of masses m naught, twice the mass, 3 times the mass. They have the same shape, size, whatever. So basically different densities. They would be made of different materials if you made this in real life. They're suspended at the same point. Rank the masses according to the periods of the pendulum's greatest first. Where's the piece we look for? So the period here that has a mass in it. But a period for a simple pendulum has no mass in it. So what did it want? Rank the masses according to the periods of the pendulum's greatest first. So since this is a simple pendulum and they're all identical, you can see here there's no mass involved in this equation, right? So the masses are irrelevant, so they should all be the same. And yeah, so mass does not affect the period of the pendulum. Um, Let me see. So again, one of the star things are always important. Simple harmonic motion is the projection of a uniform circular motion on a diameter of the circle in which the circular motion. So if you take sort of just a two-dimensional pendulum and you swing it back and forth, it looks like this. So then if we take it from the top and the bottom, and then you rotate it like this, now it's just moving like this in a straight line, right? So a lot of times in real life, these pendulums, and there's some bigger famous ones in, I think there might be one like the Capitol building, or they set one up at one time. But they have a slight angular component to it. So if you, again, look at it from up top and it's swinging like this, they usually have a slight twisting to it. And even if you don't put a twist to it, the rotation of the Earth actually affects these pendulums. So they end up moving slowly around like this, and it makes a circle if you look at the outer portions of it, right? So it keeps going around. And that's what they're saying here. We have this circular motion going around, and then you can pick out the pieces, use the geometry, and get the information, and then you can start solving equations with this, right? When they start doing like this, as you get further in physics and probably engineering, like we have, for instance, here P and P prime, essentially you run out of variables a lot of times. You don't want to use other variables, so it's showing a point, but a point two different places in time, so we're just going to designate it with a prime symbol, right, to show you that it's different, but it's the same, right? So again, we went over this before. Here is your position equation. So this is your position function. So in accordance with time, we have these pieces, and then if you take the first derivative of it, right, we did this before, you end up with sine instead of cosine. You end up with a negative sign out front and this omega portion. If you then take the second derivative of it, again, you end up with this piece. And again, we went over that before. So simple harmonic motion. So this is kind of a jump up in complexity. This is sort of like introducing air resistance to things flying through the air. It is a level of complication to it, and you get more into this the further you go when you deal with real world problems and not just textbook problems. So this is called damped harmonic motion, and they introduced this damping force, and the B is essentially how much you're damping something. So in this case, probably not the greatest real world instance. If you notice, like a door in your classroom, or usually to the entrance of a building or something like that, sometimes they'll have a spring attached. Probably not really anymore, since they don't make doors like that anymore, but they introduced those boxes with like the little rod that comes out, and that way the door slows as it gets closer. That's like a dampening force, right? It's not just a door slamming shut at a sort of linear velocity coming through it. It'll slow down as it approaches the door. They're using a similar situation here, where they say we're just going to take a spring, and then we're going to take a mass, and we're going to let it go, and it's going to bob up and down. The difference is it's going to hit this water before it hits the maximum x distance it's going to go. So the pot or container of water is acting as the dampening force. So the water has some dampening constant that we're adding down here. So when we start to model it and we start to plot it out, it doesn't look the same anymore. It's not a consistent ongoing sine wave. It's a sine wave that becomes limited. And if it was, for instance, bouncing in the water and then coming back out, you would just mirror the situation, right? It would just slowly go back up, right? Or out, depending on how you want to look at it, right? It would be, so in, out, mirror situation. And then we're taking, so it gets a little bit more complicated with the math here if you've never seen this before. This is where you're going to get in trouble with a lot of these things where people start saying, if you remember in your ordinary differential equation class, I'm pretty sure 99% of you don't know what ordinary differential equations are, or ODEs as they're called in short. You will have to take that class eventually. So you have come up here. You have, again, the Newton's second law, so you have the differential equations. So all this is saying is, we should be familiar with this. I've showed you this a couple times. This is a derivative of x, whatever that is, in respect to time, right? So this is a derivative, only it's the second derivative. So you'd have to take two derivatives in respect to time for this guy. And then you have plus kx equals 0. So the long and short is, don't worry about this too much. I'm not going to test you on it. There's not going to be no specific questions that have to do with like second order derivatives in a single equation, this kind of thing. When we do this, you get this exponential out of it over here. And you can see it's a negative and time is in there, and then this dampening force. You get this angular frequency out, and again it's omega prime because it's not just omega now. And then you get this combined piece out of this. Again, just to be exposed to it, to know what this is, so you've seen it before, you can get a brief understanding of what this is, but we're not going to get too heavily into it. So for small dampening, you can see here, basically, we're using small angle approximation stuff, so our cosine portion goes away. And you get this decreasing amplitude. So we're saying it's approximately equal to this. Not exactly. It depends on what you're using it for. A lot of real world stuff, you could just use the approximation. And then we have this. I guess I forgot to cover that up. 3 sets of values for spring constants, damping constants, mass for the damped oscillator in this figure, which I think it's not that one, it's this one. So this guy bouncing up and down. Rank the sets according to the time required for the mechanical energy to decrease to 1/4 of its initial value. So if you take these pieces then and plug them in, basically, so you get 2 k naughts, that goes up here, so this half goes away, so you get k naught. You get a single value of b naught, which is in the exponential portion, and then just this mass, which is divided by. So if you do this, you say, okay, the dampening force is the greatest in number 2, it's 6b, but then you got 4 times this m, so it's 6/4, so it becomes 3/2. So it's not quite as big as you think. And so this is 3, this is 3/2, and then that's just 1. So that's why it's saying that the slowest time is going to be this. Did I do that the right way? Rank the sets according to the time required. So yeah, this is the greatest time, this is the least amount of time. Maybe I said that backwards initially, but that's where they're getting this from. Okay, so we went over this. This is the same thing. Angular frequency of a driving force. A forced or driven oscillation. Obviously, if you have a pendulum swinging back and forth, it's going to be subject to real world things. It's eventually going to, air resistance and friction and whatever is happening in the system is going to take effect on it. It's eventually going to slow down to nothing, and it's just going to stop. If you have a forced oscillation or driven, it means like there's like a motor added to it. So possibly at the top, it's just swinging it back and forth over and over, so it never loses any energy. That motor is constantly restoring the energy back into it, so it's always moving at the same rate. So we get these equations for that, and then you just have the velocity amplitude is greatest when these two equal each other. And that's that. One more thing, so there's a resonance frequency to things. Well, they're just initially talking about resonance. Amplitude is the largest when it says this is also approximately when the displacement amplitude is largest, so when the resonance is happening. The reason that, again, this is sort of an introduction to this, we don't get a whole lot into this, just to get some exposure to it. You get into the things of resonant frequencies of things. So these are basically an ideal frequency that goes through something that makes it vibrate at its maximum. So if you look up, I probably could have looked this up on YouTube, but there was a famous bridge, I think in the 30s is when it was, but they designed it and they'll put gaps in bridges so the wind can flow through. And the problem was when the wind picked up to an exact speed, it basically vibrated the bridge in such a way that it matched the natural resonance frequency of the bridge. So it was a maximum amplitude. So this bridge is just going like this. It's insane. If you were driving across it, you would literally your whole car would have been thrown off the bridge. Obviously, people could see it was going bananas, so nobody's crossing it. Right? Someone actually just filmed it in like black and white. That it's going crazy. So this is definitely something engineers need to keep in mind. Another real life situation is in the physics building a couple years ago. They were redoing the HVAC system. So we have a lot of these large HVAC motors in certain places in the building. And one of the main classrooms we use for the physics room, there's the motor is just sitting right on top of the room. So when they were running the HVAC systems and they're putting in all this new stuff, they wanted to test the sort of maximums of it. So one day they would just have maximum heat. And this was a ridiculous time to be in school. They would run maximum heat. You'd come into school one day in the building, it'd be like 85 degrees or something crazy. And then they would run the maximum AC for a couple days, and it would be literally like 59, 60 degrees in the physics building. It was brutal to be in there while they're messing with this stuff. But while they're doing this, these motors, when they're testing these motors are going constantly and they're running full force, which they almost never do. It's for kind of like emergency situations. So while we were in the physics classroom and this thing's running at full force, the room was actually doing this, the floor of the room. So we're sitting there like literally trying to pay attention to a lecture while the room is doing this. Like people were literally just getting like seasick and nauseous from being in there, from this thing just rolling up and down. Luckily, they only did it for like a week or whatever, so it wasn't the end of the world. But you need to know this information when you design things. It's very important because it can very massively affect whatever it is you're building. And then we get the typical summary stuff, what we went through. So yeah, that's the last lecture. If you made it this far, good for you. If you're one of the last 3 people watching these lectures, also good for you. It's 1 test remaining, 1 final exam, and then you're done. Just remember, I'll make announcements too about this because again, I seriously know there's maybe one of you who made it this far. That we dropped the lowest test, quiz, homework. Those will be dropped. Also, if you get to the end and your grade is not something you want it to be, you can switch it to basically pass-fail. So satisfactory, unsatisfactory, right? So again, I'll post stuff about that. You don't need to know about that now. But hopefully you enjoyed the class. That's the end.